Welcome back, complex analysis students. Today we're going to talk about topological definitions. Soon we're going to define functions, and the domains of functions that we're going to be talking about are in the plane. We're talking about complex valued functions that take complex numbers as inputs and give complex numbers as outputs. So the domains of these functions are going to be, areas in the plane. And to describe them properly, we need these topological definitions. So let's get started with that. So the first thing we need to talk about are the so-called epsilon neighborhoods. So let's start off with epsilon being a positive real number. So the epsilon neighborhood of a point, z0, is just a little circular disk centered at z0 of radius epsilon. And the way we can describe that is with an inequality. It would be the set of points satisfying this inequality modulus of z minus z0 is less than epsilon. We can also speak of a deleted epsilon neighborhood of z0, which is a very similar concept. A deleted neighborhood of z0 is just a circular disk centered at z0, and also you remove the point at the center of that disk. So it could be described in terms of a compound inequality like this. It would be the set of points z in the complex plane satisfying 0 is strictly less than absolute z minus z0, and then that's less than epsilon. And of course, here are the pictures of the two concepts. On the left, there's an epsilon neighborhood, so it's just a circular disk centered at z0, radius epsilon, and notice the dotted line along the boundary indicates that the boundary is not included as part of that region. And we have a little notation for the epsilon neighborhood. I'm going to indicate it by in parenthesis z0, comma epsilon. You can see the deleted neighborhood on the right there. It's just the same circular disk, but it's got a hole right there in the center at z0. So that's your deleted neighborhood. It's also missing the boundary. And we'll have a notation for that too. It'll be in, and I'll put a little circle on top of z0, comma epsilon. So we want to get to the concept of talking about what are called open sets and closed sets. Now you have some experience with this probably from previous courses, like in even in calculus class, we talk about open intervals and closed intervals. So we want to expand the idea of open and closed intervals to regions of the plane. First step in that is we need to talk about interior points, exterior points, and boundary points of a region or of a set. Start off with a set S in the complex plane, and I've got, just some general set S colored in yellow over here on the right. So an interior point of the region S would be a point that you can put a disk around that point and it stays entirely inside that set S. So Z0 would be an interior point of S if there exists epsilon greater than 0, such that the neighborhood of Z0 of radius epsilon is contained in S. Graphically over here, some point like, say about here, Z0, that would be an interior point because I can find an epsilon so that the disk of that radius epsilon stays entirely inside S. So this point here would be an interior point. An exterior point is a point that you can put a disk around it and it misses the set S entirely. To put that into more precise language, we'd say Z0 is an exterior point of S if there exists an epsilon greater than 0, such that the disk or the neighborhood of Z0 of radius epsilon is contained entirely in the complement of S, C minus S. So an exterior point would be something like, let's say if Z0 were down here, just below the x-axis, I could find an epsilon here, so that the disk of radius epsilon misses S entirely. And then a boundary point, intuitively, it's just a point that's on the edge. But to be on the edge means that it's close to points that are in S, but it's also close to points that are not in S. The way we can describe a boundary point is to say Z0 is a boundary point if, for every epsilon greater than 0, the neighborhood centered at Z0 of radius epsilon intersected with S does not equal the empty set, and the neighborhood centered at Z0 of radius epsilon intersected with the complement of S does not equal the empty set. So those two intersections being non-empty means that that point Z0 is close to the points that are in S, and it's also close to the points that are not in S. So for example, if I pick this point sort of on the upper left edge of S here, and I look at look at any old epsilon neighborhood of that point, you can see that that disk is intersecting S. No matter how small I draw S, that neighborhood is going to intersect S, but it's also going to intersect the outside of S, the complement of S. So that point would be an example of a boundary point. A few more bits of terminology. So if we sort of gather up all of the interior points, and I would get a set, int of S. So this would be the set of interior points. I can similarly talk about the collection of all exterior points. Maybe I'll call that ext of S. And then the collection of boundary points, it's common to use this sort of a del symbol, so like del of S for boundary. Sometimes people use BD for boundary too, but I'm going to use this del symbol because I like it. So let's consider this example here. So the set S in question is an open unit disk centered at the origin, radius 1. Of course, we can describe that as just n0, 1. That'd be the neighborhood of 0 of radius 1. I want to know what is the interior, what is the exterior, and what's the boundary of this set. Of course, we could prove each of these assertions, but I'm not going to. I just want to kind of give you the idea of it right now. The interior of S, those are the set of points around which you can find a neighborhood that stays entirely inside that set S. And if you think about it, this will actually end up just being the set S itself. Because if I take any point inside that that disk, now if it's inside that disk, it's not on the boundary, right? Because the boundary is not included as part of that disk. So no matter where you pick that point, you can always find a little bit of distance between that point and the boundary, so you can put a little disk around it that stays inside the set. So any point in S is an interior point. And then any point that's not inside of S would not be an interior point because, well, none of the disks would stay in, there would never be a disk around such a point that would stay inside of S. The exterior, how could we describe that? So the exterior is just going to be everything that's outside of that disk. In the exterior of this set are points that you can put a disk around them, and that disk stays entirely outside of that set. So certainly none of the points right on the boundary would be exterior. So it'd have to be points that are beyond the boundary of it, right? So you could describe this as just the set of all Z, where the modulus of Z is greater than 1. And then the boundary of S would be, of course, just those points that are on that unit circle. So those would just be the set of Z, where the modulus of Z is equal to 1. Notice that any point that's on that boundary, if you put a disk around it, that disk is always going to intersect points inside S and then also points outside of S. So when you're thinking about interior, exterior, and boundary, you're always thinking about these little disks around the points and how they interact with the set. Okay, so now that we know what interior points and exterior points and boundary points are, we can define what we mean by open sets. So one way to describe a set being open is to say that it doesn't contain any of its boundary points. So we could say S is open. So how could I capture the idea that S does not contain any of its boundary points? Well, I could just say if S intersect the boundary of S equals the empty set. But it turns out there's lots of ways to capture the idea that a set is open. One of the common ways that I'm listing as an exercise here is that a set would be open if and only if S is equal to its set of interior points. And then the way the author of our textbook defines closed is to say S is closed if it contains all of its boundary points. We would write that as boundary of S is a subset of S. You may have a set that is not closed, but you want to figure out what do you need to add to that set to make it closed. And so doing that is forming the closure of the set. So the closure of a set is just where you take the set S and you union it with its boundary. So you're just throwing in the boundary with the set. That's how you turn it into a closed set, is to make sure that it has its boundary inside of it, right? And that makes sense with the definition of closed because we say S is closed if it contains its boundary. So if we've got some set S and it's not closed, then we can make it closed just by including its boundary with it. So that's the closure, and we denote it by S with a bar on top. Okay, so let's go back to looking at this example of S is the unit disk, or it's the neighborhood of 0 of radius 1. So we got this unit disk here with the dashed line on the boundary indicating that the boundary of it is not included. So we can tell this set is open because the boundary of S here is equal to the set of Z's, or modulus of Z equals 1. So we can see that S intersected with its boundary is empty. See, S doesn't contain any of those points where the modulus is equal to 1 because, N0, 1 here is the set of Z where the modulus of Z is strictly less than 1. So it's pretty clear that S intersected with boundary of S is the empty set here. Now we can say S is not closed because the boundary of S is not contained in S. The boundary is the set of Z's where the modulus is equal to 1, and that's certainly not contained in the set of Z's where the modulus is less than 1. And then lastly, the closure. How do we take that set and make it closed? Well, we just want to include the boundary, right? So if I want to take that set and include the boundary, the definition says it would be S union the boundary of S. But we could write that succinctly like this. It'd be the set of Z's where modulus of Z is less than or equal to 1. I want to make a few observations regarding open and closed sets. So you can have sets that are neither open nor closed. You could see the same sort of thing even on the real number line, right? You could have like an interval from 0 to 1 where 0 is included but 1 is not. Back in calculus class, we called this a half-open interval. So it's not open, but or you could call it half-closed. So we can have similar sorts of things happening in the complex plane. So this example here, shaded in yellow, you can see that it's not open because it includes some of its boundary, right? So I can't say that S intersected with its boundary is empty because S includes some of its boundary. In particular, those points on the top half of the circle are included in S, and those points are part of the boundary. And then also, S is not closed since some boundary points are not in S. In particular, those points on the bottom half of that circle are on the boundary, but they're not part of S because we got a dashed line there indicates that those points are not inside of S. So this one is not open and it's not closed. You can see there, you can actually give a description of that set, that's very precise, but it wasn't important for just the conceptual understanding of the point that it's neither open nor closed. Another thing to observe about open and closed sets is that open and closed are not opposites. It's not like when we use the word open and closed to describe the status of a door. It's true that a door is either open or closed. There's no sort of in between with a door, right? It's either open or closed. But when we're talking about sets, you can have sets that are not open, but that doesn't mean that they're closed. And you can have sets that are not closed, and that doesn't mean that they're open. And that example at the top illustrates that. Just because that set's not open doesn't mean it's closed, right? Because this set's neither open nor closed. So that's a common misconception when you're thinking about open and closed. In fact, going to the third point here, you can have sets that are both open and closed. For example, the whole complex plane is an example of a set that's both open and closed. Kind of a cute word for this is to call it a clopen set. I'll leave you with just a little brain teaser. Can you think of any other clopen sets? Or can you completely characterize all of the clopen sets in the complex plane? I'd be interested to hear if any of you think of the answer to this. Our next concepts to talk about are connected sets, domains, and regions. We're trying to work toward describing sets that are nice domains of functions. Now we're using the word domain here, but we're not going to be talking about domains of functions exactly right away. But the idea is we want to describe sets that are sufficiently nice that they can serve as domains of functions. To that end, the first concept that we want to talk about is the idea of a connected set. So the idea of a connected set is that it comes in one piece. It doesn't come in like several disconnected pieces, right? So the way we can describe that formally is to say the set is connected if for any pair of points z1 and z2, you can find a polygonal line consisting of a finite number of line segments joined end to end that joins z1 to z2 while staying entirely inside of the set S. So for example, that left yellow set there, you can see that you can draw a little zigzaggy line from z1 to z2, and that zigzaggy line, this polygonal line, would stay entirely inside of S. So something like that. On the other hand, the set on the right, there's no way that you're going to draw a polygonal line from z1 to z2 that stays inside of that set S. S being, the combination of those two pieces. Like any polygonal line that you would draw from z1 to z2 would have to go outside of S, right? So you'd have a little bit of a problem area there. So I think conceptually, though, the idea of connected is pretty clear. Of course, we can cook up degenerate things that are like where you have a hard time deciding whether it's connected or disconnected, like some sort of fractally set or something weird like that. But for the sort of things we're going to be considering in this class, just understanding it on this intuitive level will suffice. If you have an open set, S, that is not empty, so we want to rule out the trivial case, and it's connected, then we call that a domain. In short, domain equals non-empty plus open plus connected. If you have a domain, so a domain we know is open, but if you include some or maybe none or possibly all of its boundary points, then you get something called a region. So a region is just a domain where you include possibly some of the boundary points. So for example, in this picture at the bottom, on the left there, that open unit disk, that's a domain because it's not empty, it's open, and it's certainly connected. And then on the right there, I've included some of the boundary, the top half of the disk. So since I've included some of the boundary of that domain, I get what's called a region. And then we come to some more terminology. We need to talk about what are bounded versus unbounded sets. So this concept's pretty straightforward. A set S is bounded. That just means that we can find a disk centered at the origin that contains that set. So our set will be inside of some mighty circle centered at the origin if it's bounded. If a set is not bounded, then we say it's we just put the prefix un on it. So not bounded means unbounded. And what you could do though, since it's just the negation of bounded, you can negate that definition of bounded. There exists an R such that for every Z in S, modulus of Z is less than R. So you can certainly negate that to for every capital R greater than 0, there exists a Z in S such that the modulus of Z is greater than R. So anyway, here are a couple of examples. The example on the left is a bounded set. In fact, the capital R from the definition, or a capital R that would satisfy the definition, would be any R that is greater than or equal to 1. So maybe, for example, take R equal to 2. So that set is certainly contained in a disk centered at the origin of radius 2. And then the set on the right there is unbounded. T is unbounded. So what we're trying to indicate here, this set, it's going forever in all directions. It's just the top half of the complex plane. According to its definition here, you can see it's just a set of z's where the imaginary part of z is greater than 0. In other words, the y-coordinate is greater than 0, so we're just talking about the top half of the plane. And that's certainly an unbounded set. No matter how big of a disk you would draw, it would never contain the whole upper half plane. It's also important to just, if someone gives some sort of analytic description of a set, that you can sort of figure out what that set looks like. So here's an example. So the set S is described as the set of z's where the imaginary part of 1 over z is greater than 1. Now when I look at that, I'm not getting any kind of geometric intuition out of that. So it's helpful sometimes to be able to take that analytic description and then come up with a geometric description so that you can graph it. Let's see if we can come up with something here. So let's start just by taking z equal to x plus I times y. If that's our description of z, then we can look at 1 over z. Of course, that's 1 over x plus iy. And we can, do the trick of multiplying by the conjugate, which, when you multiply all that out, you get x minus iy over, and then in the denominator you get x squared plus y squared. And so then you could separate this out into its real and imaginary parts as x over x squared plus y squared plus, then you have negative y over x squared plus y squared multiplied times I. So that tells me that the imaginary part of 1 over z is equal to negative y over x squared plus y squared. So that's important because in the description of that set, I'm looking at the set of z's where the imaginary part of 1 over z is greater than 1. Negative y over x squared plus y squared being greater than 1, we can think about the set of x comma y's that would satisfy that inequality. X squared plus y squared would be positive, so we can multiply both sides of the inequality by that positive amount, and you'd get negative y is greater than x squared plus y squared. And then we can put everything on one side of the inequality and write it as x squared plus y squared minus, I guess it would be plus y, is less than 0. And I'm recognizing this as the sum of a quadratic in x plus the sum of a quadratic in y. So I know that those things generally work out to be circles, and by doing some completion of the square, I can figure out where that circle's centered. So in this one, I could write that as x squared plus, I'm going to do y squared plus y, then I take half of the coefficient of y and square it, so it'd be add a fourth. And so I'm going to add a fourth to both sides of this inequality. And so now it becomes x squared plus y plus half quantity squared is less than 1/2 squared. So I can see that the center of this disk is 0 comma negative 1/2, and the radius is equal to 1/2. And you see that in the inequality it's a strict less than, so what we're talking about here is a disk centered at 0 negative 1/2 of radius 1/2 that does not contain the boundary. So it'll look like this. So the center as a complex number is negative I over 2, and then you can see there that the radius is 1/2. I never would have got that from just looking at that defining inequality at the top, imaginary part of 1 over z greater than 1. But yeah, cool, it turns out to be a circle. So who knew? The last concept related to regions in the plane is that of accumulation points. This will be sort of closely connected to the idea of limits later. So a point z0 is an accumulation point, or sometimes we call it a limit point, of a set S if every deleted neighborhood of z0 contains at least one point of S. So putting that into a more symbolic form, we say z0 is an accumulation point of S if for every epsilon greater than 0, the deleted neighborhood centered at z0 of radius epsilon intersected with S does not equal the empty set. So the reason for doing a deleted neighborhood is that the limit point or the accumulation point itself need not be in the set S. It just needs to be really close to the set S. It's very similar to the idea of a boundary point. But let's it's not quite the same as a boundary point, but oftentimes boundary points and accumulation points coincide with one another. But the idea is if you take this very small disk centered at z0 of radius epsilon, ignoring z0 itself, and then if you intersect that with S, that neighborhood will always intersect with S. And you know that the intersection point won't be at z0 because deleted z0 from the picture. This is related to the idea of a set being closed, and this will be an exercise for you to try to prove. It's equivalent to say a set is closed to say the set contains all of its accumulation points. So this is another characterization of the idea of closed. So let me give you a specific example of a set where we have an accumulation point going on. So the points that we're going to look at here are points of the form I, and then I over 2, I over 3, and so on and so forth. So if you would start graphing those points in the plane, you would see something that looks like this. So you get this sequence of points, and those points appear to be getting closer and closer and closer to the origin, but of course they never quite make it to the origin. So the origin here is not one of those points. But if you take the origin, so in blue here I've got the origin, so take the origin and put any disk of any size that you want around it, and then delete 0 from that, you can see that any such disk will intersect with the set S. That sequence of red dots will eventually work its way into such a disk, no matter how small that disk is. So here I can see that z0 equals 0 is an accumulation point of S. In fact, z0 is the only accumulation point of that set. This is something that we could prove if we were so inclined, but I'll leave that to you to try to tackle if you like. I just mainly wanted to convey the idea of what an accumulation point is. You can see why it's called an accumulation point. Those red dots are accumulating there near 0, right? And you can see why this concept might be related to the concept of limit a little later. It's kind of like the limiting values of those red dots is 0, right? Okay, I think that will do it for the topological concepts for the day. And then next we'll be talking about functions. And so we'll be moving toward defining functions, and then we'll do limits. And then, of course, after limits, we'll get derivatives. So very soon we'll be doing fancy calculus with complex numbers. Anyway, I'll let you go with that. Talk to you soon. Bye now.